Hi, Eugene. Thanks for joining me today. I was hoping you could talk a little bit about both your background and then the research we'll be discussing today.
Thank you, David. So my name is Eugene Oga, and I'm a PhD student in Analytical Chemistry at the University of North Dakota. I started with a Bachelor of Science and a Master of Science in Cameroon from the University of Buea, and then transitioned to US where I'm pursuing a PhD in Analytical Chem. Originally, I have a background in material chemistry, and now I am pursuing the PhD in analytical chem because I understand that the properties, the performance of material is dependent on the characterization of those materials. And so, what I'm currently doing is with my advisor, we are employing analytical techniques such as evolved gas analysis and analysis gas chromatography to understand the properties of material, how materials break down over time, and what fragments they break down to. In a bit, we intend to propose what components of this material are losing over time, and of course, maybe make recommendations to the manufacturers on what they could possibly change over time in their process.
That's super interesting.
Yeah.
Yeah, I really enjoyed reviewing your presentation, and I was hoping you could tell the audience a little bit about what structural sealant glazing is, and then why understanding the aging process of this glazing is important.
Oh, so when you look at buildings, current buildings where they're using more of glasses and more of metals to do it, there is a need to bind these metals to the wood, to the walls, to the glasses that you are like in the construction industry. And so the thick liquid that they usually use to blend or to bind these two together is the sealant. Now, this particular sealant is important because it prevents the flow or the incoming air. Like it prevents some sort of air from getting into the building. It also helps in preventing moisture and improve the performance of that particular build or the stability of the building. So over time, the building tends to fail. It tends to age, like every other thing will age. But the problem is, studies have estimated how long sealants should last, how long buildings should last, but they do not explain how the aging, how the breakdown of these materials are actually taking place. And so it's important for us to know how these materials are breaking down over ages. And what we're trying to do is to figure out what components are being lost over time. And if these components are lost, we can then see what we can do as recommendations to fix it. So basically, it's important for us to know when the material is beginning to fail, because if we know how it is failing, we will know how to fix it. I think.
Your presentation mentioned different causes of the failure that you're seeing for the sealants. How did those different types of failure modes inform the analytical work that needed to be done?
Yeah, so if we look at failure, it could be cohesive failure, adhesive failure. Cohesive, adhesive, the two materials you're trying to use the sealant for not binding together properly, or maybe due to surface issues. But these are mere issues that can actually be taken care of if you do proper surface cleaning before applying the sealant. But if we start talking about chemical degradation, physical degradation, like exposure to UV, hydrolysis, oxidation, we start talking about environmental factors like temperature, moisture ingestion, maybe pollutants, then we need a different approach for this kind of analysis. So if we look at the physical method where it could become like cracking, some sort of fatigue and creep, um, the mechanical, dynamic mechanical analysis would give information on how the cracking is happening, on how the strength is feeling, but it wouldn't tell how much or what of that component is actually being lost that is causing that physical change that we observe. And so they will still need to do some chemical analysis. If you talked about environmental exposure, such as and moisture ingestion and all of that, there is some sort of chemical changes that is taking place in the composition of the sealant. If you also talk about chemical degradation like UV exposure, oxidation, and hydrolysis, that will need some analysis that will allow us to identify the chemical changes that are happening in the molecular structure of that silicon polymer. And so, in all of these different techniques or different failure modes and causes, gas chromatography and the mass spectrometry would be very important to identify the volatile degradation products and the changes that is accompanying the siloxane packed backbone. And so that is why we are looking at gas chromatography analysis of this product.
What modifications to standard GCMS were necessary to accommodate some of the complexities of working with the siloxane chemistry?
Now, I think this is a little bit. This is where we needed to do some checks because if you look at the GCMS column, it's also made up of siloxane, and the reason it is made up of siloxanes as well, we're using the DB5MS column, and which has about 5% polydimethyl siloxane. So we needed to check to be sure that first the column will not like the matrix effect from the column will not act as an additional product of the siloxane. But for us to be able to do all of this, we added pyrolysis GCMS because analyzing just the sample, the siloxane sample, the silicon sealant sample, well, with GC, we might not be able to get what we need. So what we do is we subject it to high temperature without oxygen in what we call pyrolysis, and then break it down and see the different products that are coming. But before we do the pyrolysis GCMS, you're heating at a full range temperature, and you want to see the products that are evolving over time. But we don't have, for us to be able to have a particular temperature focus, we then employed evolved gas analysis. This evolved gas analysis is like a fast screening technique that allows us to check at what temperature range we should be focusing on when we are doing the pyrolysis GC. So when we employ evolved gas analysis and mass spectrometry, we rapidly screen through the sample using a temperature, and then we will find a particular zone where most or all of the components of that silicon sealants are eluting. Then we will focus our pyrolysis at different steps within that temperature zone that we've seen with evolved gas analysis. So when we sequentially divide those temperature steps, that will allow us to carry out detailed analysis of those different components that have been evolved at different times.
Were there any surprising findings that contradicted your initial hypotheses about how these silicone sealants degrade?
Yeah, initially we were expecting that additives like maybe binders and all other components would be actually the main reason why that degradation is taking place over time. But what we were able to see is that there was no change in the chemistry of the siloxane, right? Basically, composition of different of sealants of the same composition was the same, but the only thing we saw was the slight shift, which is as time is going, as the sample is aging over time, it tends to move to lower temperatures. That shift is what accounted for the could account for the mismatch, the surface changes, and all of what we were observing. And so we couldn't pinpoint exactly what changed in composition, but we could see a shift in the elution of compounds that products of that degradation over time. So that shift is what gave us the information. So this is we were using EGA as a screening, which we can now say is can be used as screening, basically just to screen through samples and all of that. So we're developing a method that if you want to quickly just check through samples, you can we can just use the EGA and analyze it.
I know I mentioned that I wouldn't ask you any surprise questions, but would you be able to talk a little bit about your sample preparation procedure? What was required?
Well, in terms of sample prep, since we are doing pyrolysis, that's one advantage of the pyrolysis GCMS. If we have to do just regular GCMS, we might have to do extraction, all the other type of sample preparation techniques prior to the GCMS analysis. But the good thing about the pyrolysis GCMS is we analyze the sample as is. As it is obtained, that is how we put it in there, and we expect to see what we see. So we do not do any major sample prep. What we just have to do is take a portion of the sample, put it in the pyrolyzer cup, put it in there, observe what happens to it. So that's one advantage of the pyrolysis because it saves us the time of doing all of those preparations.
I'm glad I asked. And yeah, that explains why it wasn't a big focus within the presentation itself, although it certainly makes sense to always focus on the results of your analysis. I always ask people about sample preparation just because that can be where there's more of the unexpected problems, some of the troubleshooting comes in because they have difficulty getting to the analysis step.
Gotcha.
How do you see the field of pyrolysis gas chromatography evolving, specifically for material characterization?
So currently, apart from excuse me, apart from gene material breakdown, we are employing this method for studies of different plant matrices. We are employing this same approach to analyze lignin breakdown. We are employing this to analyze other polymer breakdown. We are doing this method for a lot. We have applications both in environment for studying pH formations and all of that. And so we are trying to extend this approach to um, everywhere possible because now if you look at the trend, if you look at how things are changing, then we expect that we should be able to apply this method even in energy, in biorefinery sectors. We waste to energy environmental monitoring because if you look at gasification systems, when they talk about clean energy, we can use our pyrolysis GCMS approach to predict the conditions that should be used for the large scale gasification systems. Because if we pyrolyze the same biomass at a very small level, and then study those basic parameters which are used in the large scale pyrolysis, we can by link or connect this and make predictions on what areas to focus on. But in terms of instrumentation, there could be an additional like improvement in the detector, fast analysis, and maybe making it portable such that you can easily move around with it and not just sit somewhere in one lab. So if that can be looked at, it will make a lot of sense. Because in our lab currently, we're not just doing pyrolysis GCMS, but we are incorporating flame ionization detector and we are also testing the impact, the new metanizer, the effect of metanizer. Normally, flame ionization detector detects everything but carbon dioxide. Mainly, it detects most organic compounds, right? But it has an issue when it has to do with quantifying carbon monoxide and carbon dioxide in products like this. So we are trying to see how an additional metanizer works by because metanizer is believed to be able to convert even carbon dioxide, even carbon monoxide, and to detect it and quantify it. So in our lab currently, one of my lab mates is working on that, seeing trying to understand how the metanizer is actually working and to prove its efficiency and its effectiveness. So if this can be extended in terms of the detectors, in terms of the applications, then it's cool. And AI is coming up. Maybe integration of AI into the system to automate some sections of this would really help.
Yeah, yeah, we will see how it goes. Is there anything else that you think the audience should know about this work?
We're not just working on sealant, like I said. So if there's anybody out there, maybe that is interested in working with us at the University of North Dakota Chemistry Department, I work with Alena Kubatova, Professor Alena Kubatova lab. And if there's need, I can maybe share the website and more of what we're doing. And then if someone finds interest in our work, it will make a lot of sense. We are actually open to collaborations because we are trying to test our methods which we are developing to see that they can be applied not just in basic environment, but it can go beyond environment. It can go up to maybe energy and different types of matrix characterization.
Thanks, Eugene. I really appreciate the time today.
Thank you very much. I really appreciate your time too.